I'm very pleased to introduce Dr. Murat Kacira. He's the director of the Controlled Environment Agriculture Center and also a professor in Biosystem Engineering Department at the University of Arizona. He received his BS degree in Agriculture Engineering from Kukurova University in Turkey, and both master's and PhD degrees from Food, Agricultural, and Biological Engineering from The Ohio State University here in the US. His research interest involves automation, environmental control, alternative energy integrated control environment agricultural systems, resource use optimization in CEA systems, including greenhouses, and vertical farming-based plant factories with artificial lighting. He is an active member of the American Society for Ag and Biological Engineering, that's known as ASABE, and the International Society for Horticultural Sciences, where he also serves as a chair of the Division Precision Horticulture Engineering under the ISHS. And with that, Murat, and just again, welcome you, my friend. And so the floor is yours. And please, the participants, pop up questions in the chat. And so we will keep track on that, and then we'll share those with Murat at any time. Okay.
With Dr. Leskovar and also my colleague, Dr. Bimba Patil, under the umbrella of International Society for Horticultural Sciences, as we have been serving as the commission chairs or the division chairs for our respective divisions. So I always admire their work and their leadership, and I'm missing our normal times and travels and meetings and discussions. Hopefully we'll come back to that normal soon again. Today I will talk about controlled environment agriculture and also precision and resources efficiency, and how do we enhance resources efficiency in controlled environment agriculture settings. As Daniel mentioned, I am with the University of Arizona Controlled Environment Agriculture Center, and this is a multidisciplinary program for research, education, extension, and outreach under the College of Agricultural Life Sciences in the University of Arizona. And I am privileged to work with a talented group of faculty, staff, and students, volunteers, and industry collaborators sharing the same vision, and that is to develop controlled environment agriculture as an economically, environmentally, and socially sustainable agricultural option. So considering the challenges due to climate change, and also the current status and availability of the resources, limited resources that we have, water, land, and other resources, and their future trends, and occasionally the concerns about food safety, outbreaks, we can expect field-based production farmers to consider and be interested in controlled environment agriculture-based production as an alternative farming, which has significant potentials with recycling and resource savings when it comes to savings for water, fertilizer, and also with less environmental pollution and impact. When I say this, I don't mean that the controlled environment agriculture will be a silver bullet and solve all the issues and challenges to address the food challenges, to feed people. What I mean is that controlled environment agriculture could be a strong contributor and complementary production practice to field-based agriculture. And we will need to see more integrated and smarter production technologies implemented to food production to address the food security challenges and enhance the resiliency when it comes to food security and also feeding ever-increasing populations. Controlled environment agriculture offers different technology levels. There are low-tech greenhouses such as hoop houses, high tunnels, or medium-tech greenhouses where we would see some mechanization and automation integrated, or high-tech greenhouse operations, either on the ground or maybe on top of buildings in close proximity to markets in urban settings. But also we can consider indoor vertical farming systems in a highly confined, controlled environment, either using shipping containers or maybe warehouse-based indoor vertical farming systems. We have to consider controlled environment agriculture and technologies as adaptive technologies. The technology should match the demand, the expectations of the consumers when it comes to quality of the produce and also market demands. The expectations of the grower or the user, the operator, their skill sets. So we have to really consider an adaptive greenhouse or adaptive controlled environment agriculture technology to achieve a sustainable and economically viable production practices. Why controlled environment agriculture? There are various reasons that we should consider controlled environment agriculture. I'm not going to list and talk about all of those. They're listed here on the slide. We can save resources, we can recycle resources, control the environment, and enhance the production quality and consistency. We can achieve consistency in terms of the products coming out of the controlled environment agriculture systems. There has been increasing interest in terms of farming technology, market, and investment going into controlled environment agriculture. The indoor farming technology market was valued at 23.8 billion back in 2016, and it has been projected to reach to 40.3 billion by 2022. Just 2000 alone, 4 billion investment went into agriculture technology sector. That is up about 2.8 billion considering 2019, and about more than $500 million investment was introduced or came to the controlled environment agriculture in the United States. Again, with greater potentials when it comes to water use efficiencies in controlled environment agriculture systems compared to field-based agriculture. And when you consider a vertical farm, indoor vertical farming system compared to field-based agriculture, it can achieve a significant amount of resource savings, for example, water, along with that nutrients, with high resource use efficiencies and capabilities. The bottom line in any type of agricultural production system is the resource use efficiency, achieving high and optimal resource use efficiencies. Resource use efficiency means or refers to the ratio of the output, and that is the yield from the production system, versus how much resource that goes into the production. This could be electrical energy, this could be water or labor or other fertilizers or other types of inputs that are required. For a controlled environment agriculture system, the main inputs are energy, the water, the carbon dioxide, the fertilizers, and nutrient and labor. The outcomes or the outputs from the controlled environment agriculture system could be edible biomass and not edible biomass, which can be recycled, actually, maybe turned into maybe an input that can be utilized back in the system and as part of the production, as well as nutrients and water. And through recycling, with proper systems integration, we can recycle water, we can recycle nutrients, and also transpired water in the atmosphere that can be captured and harvested and fed back to the production system, so we can achieve greater resource use efficiency in the production. We have complete control on both demand and supply conditions in controlled environment agriculture settings. However, we need an understanding, a detailed understanding of how plants interact with their environment, with their surrounding environment, and that is essential for improved climate control strategies and also for resource management as part of an improved crop production in controlled environment agriculture settings. Either greenhouses or other types of indoor agricultural systems this is a complex system where there are various processes that are occurring at the same time or can occur at the same time. The heating, cooling, transpiration, watering, fertilization, and other processes that are relevant to crop production. And all of these processes must be orchestrated in a way that the system is performing at the optimal level, as well as with greater and optimized resource use efficiencies. So we will need to consider combining the controlled environment agriculture systems physics along with the crop physiological information to improve the environmental control and also to achieve greater resource use efficiencies. Traditionally, the environmental control has been focused more on sensing and monitoring from an aerial environment or maybe from a root zone environment when it comes to controlled environment agriculture systems. However, with now the systems becoming more data-centric, agriculture is becoming more digital and data-centric, we are going to focus more and more on relying on data, also considering plants and plant responses that should be integrated into decision-making and also should be considered as part of the environmental control and management applications. Automated crop diagnostics and decision support systems are among emerging and developing automation technologies. With computer vision, machine vision applications, bringing direct information from the crop and crop canopies regarding to crop health, as well as growth information. So this information can be included as part of the decision-making process. So our center has to be on the plant as a starting point, and also considering other processes and environmental control aspects. As such approach, considering plant response-based decision-making and environmental control in a way as a speaking plant approach has been our emphasis in our research programs. As you can see here, we have developed a computer vision guided plant health monitoring system where a multispectral signature from the plant was obtained and used to detect stress symptoms from the plants before those symptoms are visible to human eye. So integrating multispectral sensing, we were able to establish timely water stress detection and crop health monitoring that could help an operator to enhance their environmental control applications and also optimize resource use and resource use efficiencies in a controlled environment agriculture setting. Labor is one of the significant input when it comes to controlled environment agriculture. We will be seeing further and more robotics integrated and automation integrated to controlled environment agriculture systems, because greenhouses and vertical farms provides that opportunity for robotics and automation integration. There are repetitive processes that a robotic system can take advantage of, or the system design can incorporate robotics into the production practices. The challenge so far, especially when you consider greenhouse production, has been the speed in terms of managing the crop, for example, with harvesting or crop management practices. But now with the technology advancing, computational speed and capabilities that are advancing with data analytics and big data and cloud computing, now we will see faster and further integration of automation and robotics into controlled environment agriculture systems. Greenhouses have been around for many decades, and the technology has reached to a maturity now in the greenhouse-based industry and crop production. We have been seeing greater interest now more into indoor agriculture-based systems, either using shipping containers or maybe warehouse-based plant factories and vertical farms. And here we are looking at some of the large-scale vertical farming operations in the US. However, we also see challenges and also opportunities to enhance the economic viability of indoor agriculture, vertical farming-based systems. The challenges have been more on the required energy, electrical energy, to run and operate the lighting systems, as well as the electrical energy needed for the air conditioning applications. And because of the nature of these three-dimensional multi-tiered systems, the production was more focused on leafy greens or microgreens, but now we're seeing interest and system designs and operations considering some of the fruiting crops, as well as we look at future of the indoor vertical farming operations. So recognizing this challenge and the potentials for improving these system designs and operations, we are working in our multi-state project funded by USDA and NIFA through Specialty Crop Research Initiative project to co-optimize environmental variables and to develop models, environmental control applications, and alternative designs to enhance the economic viability of the leafy green production in vertical farming-based indoor agriculture systems. Our research in the University of Arizona has been going on in our urban agriculture vertical farming system based facility. This is a student-led facility and operation and research programs from its design and all the way to the research also applications. Our students, graduate students and undergraduate students are closely and heavily integrated to our ongoing research activities. And we also appreciated the participation from our industry collaborators, and we always appreciate their contribution and support. So far, our research focused more on the development and optimization of the environmental control aspects, trying to find mechanisms to control some of the significant variables leading to resource savings. For example, one of our recent research with Brian Kaplan, a former master's student from our lab, developed and optimized daily light integral and carbon dioxide controls for lettuce crop production in vertical farming settings, with emphasis on electrical use efficiency. As you can see, we can control the crop yield by controlling the light intensity or the accumulated light delivered to the plant with elevated yields as you increase the light intensities. However, that brings the need for electrical energy use. But at the end, when you consider electrical use efficiency or resources efficiency, then you can see that they're almost identical or very similar. So we need to consider how much yield that we can accept or within the acceptable limits versus also controlling the amount of electrical energy input that goes into the production. So these type of decisions can be made leading to conserving resources when it comes to vertical farming operations or controlled environment agriculture systems operations. In indoor vertical farming systems, one of the main challenge is also the non-uniformity of the environment, considering the multi-tiered systems and with the lack of space between the lighting systems as well as the plant canopy. The air can stay stagnant in specific zones, again leading to inadequate or non-uniform airflow and ultimately non-uniform environmental conditions when it comes to the temperature or the humidity or the carbon dioxide distribution, as well as the air velocities or current speed that we would like to achieve above the canopy zones. So the airflow, the proper airflow is needed that can enhance plant transpiration. With enhanced plant transpiration, that can increase the transport of nutrients at optimal levels, so we can manage the concerns because of the nutritional deficiencies that are commonly observed when it comes to especially leafy greens production, particularly with lettuce, with tip burn occurrences. So these is one of the main challenge that we have been observing in vertical farming systems. So in order to overcome this issues with tip burn and the lack of airflow and uniformity, there's a need to reduce the boundary layer thickness with the proper airflow, so we can enhance the transpiration process to support the nutrition, the uptake of calcium to prevent the tip burn occurrences. We can consider alternative designs when it comes to air distribution systems. However, testing them and experimenting with them with a greater number of possibilities is economically not viable. It's cost prohibitive, and also it can take a long time to evaluate such alternative design. So for the past several years, we have been focusing on using computational modeling and simulations using computational fluid dynamics, where we can develop a model and validate it, and after validation and accepting the accuracies of that model, then evaluating various scenarios and system designs are possible in a very short time period with greater details available for the user or for the designer when it comes to the uniformity of the environment or some of the what-if scenario analyses and design optimization. So Ying Zhang, one of our former lab member, has been leading this research effort in our lab, and now she is with the University of Florida Agricultural and Biological Engineering Department. Our emphasis and focus has been more on localized climate control, bringing the conditioned air closer to the canopy through a unique system design, so we can optimize the air uniformity or environmental uniformity with the air conditioned air being brought to each individual tiers in the vertical farming systems. We have been able to publish some of these research efforts in collaboration with our colleagues, Dr. Toyoki Kozoi, as well as Dr. Genwan New, with several textbooks. Our chapter has been published in the one of the recent Smart Plant Factory book, but I'm looking forward to actually publishing our new research efforts with a team of colleagues in the upcoming edition of the Smart Plant Factories with Dr. Genhua Nu and as well as Dr. Joe Masabni, as well as Dr. Kozai. There's always questions about the energy use when it comes to greenhouse operations and indoor plant factories. In a recent research, we focused on this comparison, considering various climates with hot and dry, or hot and humid climates, or cold and dry climates, to evaluate the energy use and efficiencies between greenhouses and indoor plant factory systems, and also try to find ways with environmental control so we can improve resource use efficiencies. In this research, as you can see, we considered the efficacies of the LED lighting systems with 2, 2.5, and 3 efficacies with LED lighting systems. And as you can see, as the lighting system efficacy is increased, then the efficiency of the indoor vertical farming systems are greater. We have also considered the number of tiers that can be considered in a plant factory setting. As you can see here, we have 2 layers or 2 tiers of plant factories with 5 tiers or 11 tiers. And as you can see, as the layers are increased, there's a linear relationship in terms of the amount of energy required to operate the vertical farming systems. But in this effort, we also considered the integration of economizer modes, where the system, the air conditioning system, can consider the favorable climate or the weather outside and bring that cold, for example, air into the air conditioning system and take advantage of that to reduce the demand for cooling loads in a vertical farming system. As you can see, with the economizer modes and more advanced environmental controls for any given multi-tier system applications, that brings the potentials to save energy compared to non-economizer mode based vertical farming environmental control applications. So at the end of this analysis, based on the locations or the climates we considered and the technology or the systems we considered with the greenhouse as well as the vertical farming system, we observed that the vertical farming, indoor vertical farming based systems were showing greater or higher resource use efficiencies or electrical use efficiencies compared to the greenhouses operating in colder climates based on our selection, but with less energy use efficiencies when you compare to greenhouse-based systems in warmer climates where you have the advantage of using the free energy of the sun for the crop production. So these are the kinds of focus and research directions that we'll see more, looking into ways and what if scenarios to integrate into environmental controls or the system designs or crop management practices so we can enhance the efficiencies, resources efficiencies in these indoor vertical farming systems, and also consider, of course, the expectations or the local climates, the local markets, because in some of these locations, for example, in Middle East and other places, the cost of electricity is fairly cheaper compared to the concerns in terms of the access to water or the availability or the quality of the water for crop production and also for food security concerns in those locations. So again, the demands as well as the technology selection should match. So we need to consider really the adaptive technologies and more so the integrated systems. Again, we can integrate both greenhouses and vertical farming systems in a given site or for operations so they can be complementary production systems. I imagine the future controlled environment systems using plants and actually plants controlling their environments when it comes to environmental control. So we are focusing on phytometric or biofeedback-based decision support and controls in indoor vertical farming based operations. Casey Shashdin is a master's student in our research lab, is leading this research effort as Casey considers multispectral imaging as well as computer modeling to predict crop growth or biomass production, so the information then can be fed into the environmental control system, or the information can be provided to the user and operator to make adjustments in real-time basis. We are looking into, again, validating and enhancing the modeling capabilities here, and also using these modeling effort to analyze several what-if scenarios. For example, the changing the CO2 control, or the dynamically controlling the CO2, or maybe the daily light integrals or the light intensities, because for a given or an expected fresh biomass, we can control the CO2, maybe alleviate the CO2 or reduce the light intensity to be able to target or achieve the same amount of fresh biomass from the production system. And the cost of injecting CO2 or using CO2 is cheaper or less costly compared to the electrical energy or the cost of running the lighting system. So we're considering that kind of environmental controls when we look at the designs of these multi-tier systems, as well as the next generation environmental control applications. We are also working on dynamic CO2 optimization, considering maybe the injection or the enrichment during specific growth stages of the crop, rather than starting with a set injection from the transplant all the way to the harvest stage, and trying to identify if there is any resource saving capabilities in that sort of approach in environmental control aspects. Crop phenotype, crops respond to their environments. So the crop phenotype is a function of their genetics and the environment, environmental controls, and also management practices. So we have to focus on the critical indicators that is characterizing the crop growth and quality. So sensing, monitoring, and some of the control capabilities should consider these, for example, fresh and dry rates, or crop height, leaf expansion, canopy expansion, relative growth rates, or maybe some of the crop produce quality aspects through sensing and monitoring applications, and integrate that into the environmental control applications. We can improve or enhance the phenotype or the outcomes from the production through engineering and maybe design optimization on the environment, and as well as management applications. But we will also need the enhancement and developments from the genetics and genetic improvements, so the crops can realize we can achieve a greater and optimal use of resources when it comes to maybe the use of light, or the lighting use efficiency, or maybe resources efficiency, water, or nutrient uptakes. So the biology has to work with engineering hand in hand, so we can achieve the economic viability and sustainability of the production in indoor vertical farming systems, and also in other types of controlled environment agriculture systems. The LED lighting brought a significant amount of opportunities for horticulture. We have to consider the efficacies and the controllability of the LED lighting systems for commercial and economic operations. We need to differentiate between research capabilities and also practical commercial applications. The way we define the wavelengths, we need some sort of standardization, and what spectrums to consider for design and maybe for manufacturing for growers, because general spectrums are easier and lower cost versus broader spectrums for specific or targeted applications. For example, enhancing flavor, enhancing nutrition, and maybe achieving high value or production and economic improvements there. So we have to consider all of these when we base our decisions for the LED lighting systems applied in controlled environments, and also the return of investment. Fixture designs or the canopy architectures that could realize the optimal light use efficiencies. Of course, we need to support all of that with breeding and enhancing the genetics and the breeding processes for the optimal light use efficiencies. In controlled environment agriculture, we will need to consider circular systems, integrated systems where we can leverage maybe a waste stream coming from one of the production system and leverage that and use that as an input for the other system, so we can recycle resources to enhance the sustainability and improve the resources efficiencies and also economic viability. So we have research programs where we are focusing on integrating mushroom production in controlled environments, where we can leverage the excess CO2 and bring that CO2 as a resource in the leafy greens production system, and from the leafy green production systems, potentially harvesting or leveraging the humidity or the water content in that environment and bringing that into the mushroom environment where that is needed. So we will see a more integrated systems like this as we look at future controlled environment agriculture systems. Internet of Things, cloud-based computing or services for data access and management has been advancing. So we will see further integration of IoTs and cloud-based services for environmental controls and providing that access and information to the growers and also the users. Augmented reality and virtual reality will be further integrated into controlled environment agriculture systems to bring the physical environment and connecting that with the virtual environment and providing that unique experiences and capabilities to the operators and growers. Maybe the consultants will be the future, and some of the systems integration that we'll see in controlled environment agriculture. Can AI do as well as a grower? We have seen some potentials and opportunities here, indicating the use and possible and positive use of artificial intelligence. I don't see that the artificial intelligence will replace the green thumbs or the grower, but I see AI as a great technology to enable and empower the grower and the production system to enhance production capabilities and also resource use efficiency. So we'll see further interest and growing interest in integration of AI, data analytics into environmental control applications. I envision future greenhouse systems to be able to generate and further generate their needs for the energy. We have been focusing on energy producing greenhouse concepts with off-grid greenhouses integrated with photovoltaic systems, either traditional opaque photovoltaic systems installed on the side of the greenhouse, providing energy needs or powering the greenhouses, as well as with other innovative systems or technologies using luminescent solar concentrating based photovoltaics, so the wavelength selective photovoltaic systems, as well as recently organic thin film plastic based photovoltaic systems. Combining the food production with energy production in the same footprint will further enhance the sustainability of food production in greenhouse systems. There are locations, there are climates, and and communities where we can consider off-grid greenhouse systems in those remote and challenging environments to support the growers or the need of the communities for food production and for their well-being. That research has been part of our recent NSF NRT funded Indigenous Food, Energy, and Water Security and Sovereignty project, where we are collaborating with a multidisciplinary team of researchers and aiming to develop and integrate and implement and educate the local communities in terms of off-grid water treatment systems, as well as off-grid food production systems for indigenous communities. Because indigenous communities are challenged with access to potable water as well as electricity in their localities. In our case in Arizona, considering Navajo Nation, our partner and our partner institutions and communities in this project, the Navajo Nation communities, the 30-35% of the communities are lacking access to potable water as well as the energy in their communities. So through this research, we are also working with our students, graduate students. That's part of the our main emphasis in this project. And they are learning, they are being educated about off-grid food production and water treatment systems, and they will be the educators of the future generations and communities in indigenous communities and other communities that are challenged with the food production or they are considered to be a food desert. We also have other research activities that are unique and working with innovative technologies. My colleague, Dr. Giacomelli, with his team, has been working on quantum dots-based wavelength selective films that are suited for space-based horticultural systems. But we are also seeing great potentials with this technology and approach that are suited also for earth-based greenhouse systems and applications. We will need to really look into capturing these kind of capabilities, wavelength shifting, multi-wavelength based films or technologies, lighting systems to enhance or achieve unique capabilities when it comes to the production quality and also resources efficiencies. We are interested in alternative proteins and produce in controlled environments. My colleague, Dr. Barry Pryor, is leading our mycology-based research and mushroom production research in controlled environments. We are looking into unique system designs and control applications, advancing the mushroom production with automation and also environmental control aspects to improve the resources efficiencies in mushroom production operations. We are looking into circular systems, trying to leverage food waste, which is a major concern also, and trying to convert that food waste into a resource that can produce proteins or other food products. And my colleague, Dr. Kaugi Davido, is leading our research programs here at the Controlled Environment Agriculture Center to convert food waste into edible insects that can be considered for human consumption, as well as, for instance, for as a feed for aquaculture-based systems or applications. As we are focusing on earth-based food production systems in controlled environment agriculture, our center has a long history of working with bioregenerative life support systems and prototypes for Mars lunar greenhouse based systems. We are currently funded by NASA, where our emphasis is more towards crop production capabilities or enhancing crop production capabilities in microgravity environments. So our team at the University of Arizona is one of the 5 funded teams in the US in this opportunity, as we are designing and testing and evaluating our production system, with main emphasis being the efficient delivery of the water and nutrients to the crop in the microgravity environment. So we're very excited about this research and also our collaboration with our international partners and colleagues in this research. we will need to grow our programs. We will need to continue educating future farmers and engineers and leaders of controlled environment agriculture in the industry. We are proud of our graduates. They are making a huge difference and impact in the industry, and we have to continue meeting the needs and expectations of the controlled environment agriculture industry. As we are growing our programs, we also appreciate the collaboration that we have with our colleagues from other institutions where we have controlled environment agriculture programs. So I would like to also congratulate you and your team at the Texas A&M University with your investment and resources going into the urban agriculture and controlled environment agriculture programs at the Dallas Center. So with that, I would like to stop here, and I would like to also acknowledge the efforts of my colleagues, faculty, staff, and students, and our collaborators, industry collaborators, supporting us with our educational and research programs here at the Controlled Environment Agriculture Center. So with that, thank you so much for the invitation again, and I will be happy to take some questions and have a discussion with you. Thank you.
Thank you, Murat, for the great, excellent presentation, very comprehensive and very enlightening. And so the floor is open. I'm not sure, I have not looked at the chat. Maybe Trish can go over on that. No.
I can't answer the chat. There's nothing there thus far. So
okay. Is there any question from the floor?
Yeah, absolutely. Thank you, Dan. That's a great question. So it's really actually counterintuitive to integrate a system that is preventing the light transmission on a greenhouse system when you consider photovoltaics applications. But there are unique capabilities when you consider organic photovoltaic films or thin film photovoltaics or luminescent solar concentrators. They come with different specifications when it comes to the shading effect or transmissivities. For sure, the one that we recently worked with, the organic photovoltaic film technology that we used, had about 30% less transmission in the photosynthetic active radiation range. But I think the consideration should be what are the requirements for the crops that is being grown when it comes to the light intensities or the qualities in that environment, or the coverage ratios. We have been evaluating that with 20% or maybe 10%, 50% coverage. So what happens when you do that in terms of the yield output or in terms of the power production, energy production capability. So those are the kind of questions we are asking ourselves in our research programs.
Murat, I have a couple of questions. When you started your discussion, you began with some challenges in relation with food safety outbreaks. That's that could be. That food safety outbreak obviously is critical in open field production. Where within the control environment or indoor ag, which are the challenges related to safety, contamination that could involve pollutants or any other some gases or what if you had to say major challenges that someone needs to be considered. Typically, you don't have that many, but when you have, it can be really pretty strong. So,
right, absolutely. Thank you, Daniel. I was referring to the outbreaks and food safety concerns, mainly actually coming from the field-based open field operations. in the presentation. So because of that, the greater potentials and capabilities of minimizing and preventing the challenges with when it comes to food safety and outbreaks in the controlled environment agriculture setting, because we have some control, right? We have controls over those challenges. This doesn't mean that in controlled environment agriculture, we may not see that a challenge or issue, because greenhouses, depending on what type of technology or technology level is used, you may have some disturbance from the outside or the pests, interfering with that production system. Or maybe a vector or a disease or a virus being transmitted through, again, insects or pests. So there are ways to prevent that, of course. So the focus should be around those challenges, and also properly designing, implementing strategies and technologies into the system designs and control aspects. Of course, the working of the operators and users, and following good agricultural practices, the hygiene, these should be in place to further prevent the concerns when it comes to food safety and other types of food safety related outbreaks in also controlled environment agriculture systems. I think the standardization and following standard procedures are needed to quantify, to monitor, quantify, and also report these in controlled environment agriculture settings. Maybe considering sensor integration into the controlled environment agriculture system, specifically monitoring the some of the variables that may give indications, that may signal indications about the food safety related aspects that can further enable and enhance our capabilities in controlled environment agriculture. So there's a need, there is an opportunity there also to further enhance, again, the food safety aspects in controlled environments too.
Thank you. Yeah. I have another question, if may not be other. So in your design, you showed excellent examples of different designs of greenhouses, and I don't believe that you mentioned designs that like maybe capturing some heat losses, and then you have the diagram, you have the arrow pointing from the floor out. I'm sure you have heard about these geothermal designs that can be potentially used to generate this heat back into the system, especially for cooler climates, and potentially take advantage of the cooling of the soil that radiates into the greenhouse. What's your view on that? And then the second is related to that. How do you think how applicable could be some of those systems in very hot environments like southern Europe? I mean, like your environment, but ours is hot with humid. It's not like hot and dry like Arizona.
For sure. There are specific, I think, applications and locations where you can consider geothermal-based systems that can help and support the environment or energy requirements for the environment control requirements for the greenhouse systems, or maybe for the indoor vertical farming based systems. I think taking advantage of the storage or buffer capabilities of, for example, earth or ground, if this is a ground-based geothermal system, or air-based geothermal systems. I think the focus should be on the demand of the energy, the system itself, the technology that is being used, and the footprint, the size that can be matched with the geothermal systems applications. So again, this should be a discussion for an adaptive technology, and with the greenhouse or the vertical farm, and also what is attached to it in terms of the hardware or the environmental control systems or the energy systems that are considered. geothermal, solar. These are all possibilities for a specific climate, location, and the system that is considered for that market and the production.
Thank you.
Murat, this is Bimu. Excellent presentation. So one question I have is, you mentioned in your presentation that some of these controlled environmental conditions will enhance the flavor along with the phytochemicals. Other than Thierry Couberto's work, are there any strong evidences that the controlled environmental conditions will enhance the flavor of vegetables, specifically in tomato and other crops?
Yeah, so that's a great question, Bibo. Thank you. That is the beauty of controlled environments. You can control the environment to control the quality of the produce, in addition to the yield. So controlling the light now with these with the LEDs, light quality, different spectrums, considered in enhancing the flavor and nutrition. For example, in the UV range, for instance, that can further enhance the vitamins or secondary metabolites and the flavor, or maybe the coloring of the leafy greens. With tomatoes, you can also control other environmental variables, maybe controlling the electrical conductivity, or maybe providing a little bit water stress to the plant. The stress is not always a bad thing, right? It's sometimes it has the benefits when it comes to flavor and the nutrition. So stressing the plant with electrical conductivity or water, right? So stress that can help also enhancing the flavor, or maybe the lycopene levels, or the taste with tomatoes. These are the types of capabilities, I think, in controlled environments, and there are a lot of opportunities there with lighting, with other control aspects that can help us.
Thank you.
Mm-hmm. Absolutely.
There is one more question. Maybe we have time here. Maybe, and then
There's one in the chat box.
Yeah. So
did you see that?
Yeah. So Murat, the question is, and this is a good follow-up from Bimu's question. It's about the phytometric feedback systems.
Yeah.
Are they capable of optimizing both, yield, productivity, and quality? If not, do you see any possibility for them to be designed to co-optimize yield and quality?
Yeah, that's a great question. Thank you. I think I want to say both. So the objective should be both to control the yield or enhance the yield, as well as also the quality of the produce. So since now we have the capability to work with LEDs and with different lighting spectrums, so depending on the observed or the signature or the information coming from the plant through computer vision or other types of contact or non-contact sensors, the system can use that information maybe to change the wavelength or the spectrum of the light, maybe to give a little bit more blue, or maybe some far red, or maybe red, depending on the objective again. We can control the blue to keep the plants more compact and shorter. We can give it a little bit more, far red and red to stretch the plant, or considering the combination of these spectrums. Those are all possibilities, and I think we have some research coming from different research lab, not from other institutions as well around the world, really looking into these capabilities with plant response-based sensing and control. Speaking plant approach has been around for many decades. The challenge has been the computational capabilities or the cost of the sensors, but now we have already overcome those challenges. So we will see further developments in speaking plant. We will see more data-centric approach to really base our environmental control and empower the grower, empower the production system. So I believe both, yield and quality, and ultimately the resource use at the end.
Excellent.
Yeah, can I ask a question? Is there enough? Can I have an opportunity?
Yeah, I'm okay.
Okay.
Go ahead.
So,
Me too.
So this is Luis Neros, professor in the Department in Horticulture. Professor Murat, I mean, I really was impressed by your presentation. Very nice. I do have a question. Not sure if it's too simple, but considering some of us working on some of these stress responses on plants, and understanding that there is a very complex system of crosstalks about from signals and the different pathways involved. I mean, it's very complicated. So my question to you is, considering all the advances that have been done in the controlled environment systems, which takes into consideration all the factors you mentioned, but when it comes to the plant itself, from the molecular point of view, from a physiological point of view, do you think that there's still a gap that has to be filled to better understand how the plant responds at that level, between signals, between pathways, and by doing so, it would make easier to understand how control environments could actually work on the plants? Do you feel that there's still a gap there?
For sure, yeah, thank you. This is a great question, actually. Yes, so plant is a very complex system. I'm an engineer. I also understand plant physiology a little bit also, but definitely we need to further dive into the plant's response to specific environments and unique environmental conditions. There's so much interest on developing recipes, meaning light, quality, intensity, EC, pH, temperature, CO2, water in the air, humidity, and how plants respond or specific varieties respond to these conditions. We will definitely need to develop further our understanding of that complexity, and plants respond to stress conditions also differently, or sometimes you may see a same signature maybe coming from different stressors. So there are some commonalities also that we need to differentiate. That has been one of the bottlenecks of the speaking plant approach, because you may see a signature, maybe yellowing or some chlorosis in the plant leaves that may come from maybe a specific macro element, or with the same signature. So similar signature at some point. So we will need to use, I think, more of these AI, machine learning, neural networks to further analyze big data sets and develop further understanding and also develop strategies that can be implemented into the production and management applications and control applications. Yes, there is that need, there is that gap, I think, but that brings up opportunities for us as well. So that's a great question, and there's so much interest and focus there, for sure.
Thank you, Professor.
Absolutely.
Thank you, Murat. Again, on behalf of all horticultural science at TMU, we're very happy to have you. And I pass to Trish for the closing.
Thank you so much, Daniel. I really appreciate it. It's been an honor to be with you today and present before you. And I hope to again see you soon in person.